but the purpose of this meetup, this kind of spawned naturally out of some like Denver co-hacking, kind of ETH programmer friendships. And I think really, I was thinking like, there's so little information out there when it comes to like Solidity and programming best practices, and everything's fragmented across the internet. Like, it was really hard for me to kind of climb that ladder of knowledge initially. And so like, I'm really into like co-learning and checking stuff out with each other and asking tough questions and asking dumb questions and just figuring it all out. So I think like, we really wanted to start something like this so that, yeah, we all could just learn better practices together. Because if we believe in decentralization and building these like powerful immutable programs on the blockchain, then we better do it right. It's like we almost have like one shot at this. So we need to stop messing around, build mature software, teach each other how to build resilient programs and how to be better devs. So it sounds a little serious, a little mysterious, but I think like genuinely like it's just fun to meet up and go through code, and that's just an accelerated path to learning is watching someone else step through code and having different ideas bounce off the room. So I think we'll see how this one goes, but we were thinking of maybe doing this like once a month, maybe once every 3 weeks if it sticks with people, get like a group going. Get people who are kind of on the just learning track to learning more and hopefully writing their own stuff.
A little bit higher.
The university published another fork. Here we go. All right, Tornado Cash repositories. An archival fork of the Tornado Cash GitHub. All right, here it is. So here's all the stuff. So most likely, let me blow it up. It's going to be in the core contracts. So, this is going to be a good one. I'm going to put on my VPN before I clone this bad boy. All right.
That's why the lights are off.
Yeah, that's why the lights are off. That's how VPNs work. Yeah, you're right. Okay. So, what I'm thinking for this meetup is we can go through the README, go through like a high level architecture, and then look into some of the contracts and the circuits. How we're gonna do this is, if you have any questions or if anything doesn't make sense, please stop. It doesn't matter if if you're in the written one line of Solidity camp. But like stop us. Be like, hey, like, what does this mean? I'm sure someone else has a question. Part of like, I feel really strongly that like part of good Solidity is like not trusting your assumptions at all. So in other programming languages, you can almost like kind of get away with not knowing what happens at the bare metal level. But if we're gonna make like programs that work resiliently and don't have exploits, we need to know what happens kind of around every corner with our smart contracts. So just to say, want to encourage just jumping out, asking questions. I'll simmer on stuff a little bit, so we'll kind of go through line by line. We'll simmer on some stuff, and then we'll move on in the code base. How does that sound to you guys? Cool. Sweet. All right. So I'm going to pull this up in VS Code here. I've got a couple extensions that I want to throw in the HackMD. They're ones that I use to audit smart contracts and just understand what contracts are doing. So the first one is going to be the Solidity Visual Developer one. I'm going to copy extension, and I'm going to put all this stuff in the HackMD. So here's that first link. So this is perfect. There's that. So that will allow us to get some really nice highlighting for VS Code to even see an outline of the smart contract before we even start to peel into it. And it's, can only recommend. So let's start with the README here and walk through Tornado Cash briefly. Let's see what they say here about like the technical details. So to give like a brief intro, like I said, Tornado Cash is a tool that, well, I guess who here is familiar with Tornado Cash already from a show of hands and what it does and why it does it? Okay, all right, cool. So to catch everyone else up, Tornado Cash is, like it says here, a privacy solution. So normally when you transfer tokens across the blockchain, you obviously have that like that layer of that viewability layer where you're able to see like, okay, 1,000 tokens went from wallet A to B to C to D to E, right? Like it's probably obvious that there's some sort of connection there, right? And that's a huge part of chain analysis is that like if you're trying to find a criminal, you analyze kind of their rabbit trail of transactions and the rabbit trail of deposits going from one wallet to the other. So things are, anonymous on the blockchain insofar as they're not bridged. And then once you've got an asset that bridges to Coinbase or Kraken or whatever, you just have to subpoena the Coinbase or Kraken or whatever ramping service, find who the KYC data of that address is, and there's your bad guy. With Tornado, or your guy who just wants privacy and to not have his people be knocking on his door. So where Tornado Cash comes in is it allows you to put all your money, all your tokens into a pool with other people. This pool does not manage permissions or amounts like vaults. So vaults, like in DeFi, is kind of a similar thing where I'd put my tokens into a vault, but me doing that, I get an assert, like it says, hey, like this person deposited 1,000 tokens, so I can withdraw my 1,000 tokens at any time. With this kind of pool, you get a special note back that says that you own up to a certain share of tokens inside of that pool. You're eligible to withdraw a certain amount of tokens from inside that pool. But no one else knows it except you because it's a private note. That private note is created. It's something called a zero knowledge proof. So it's this portable little mathematical proof that you can take anywhere and prove that that you've computed something honestly, right? So you knew all the inputs to something, and that would allow you. This privacy gadget would then allow you to withdraw because you have a valid proof. So it removes the linkage between the person who input the token and the person who withdrew the token, if that makes sense. So let's just briefly look through the README here. Tornado Cash is a non-custodial Ethereum and ERC20 privacy solution based on ZK snarks. So that's exactly what it says, breaking the on-chain link between the recipient and the destination. It accepts ETH. It accepts ETH deposits that can be withdrawn by a different address. Whenever ETH is withdrawn by a new address, there is no way to link the withdrawal back to the deposit, ensuring complete privacy.
Just a real quick thing. I might be totally wrong here. It wasn't like Monero, weren't they all about like security and privacy as well?
I'm not sure. I don't know anything about Monero.
Yeah, it's all about that, and that's why, as a U.S. citizen, it is very hard to get Monero on any exchange.
So true. So let's just walk through real quick here how. Yeah, let's walk through here like how the flow works. I think like as with the rest of like programming, it makes sense to understand things from a user story perspective and then break them down into elementary parts afterwards. Okay. All right.
Would it be worth talking about some of the legitimate use cases
for having a privacy-preserving wallet, like anonymous crypto?
In case anyone's listening.
Yeah, in case anyone's.
Oh yeah, no, this is for educational purposes
Yeah.
only.
No, but there's a ton of, like, I know a lot of devs who launch smart contracts who like to do it from a clean wallet. That way, people can't try and snipe their contract or know when they're doing a new token launch. So if you do it from the same wallet, it's pretty easy for, like, bots to follow you.
Yeah, no, this is correct. Like operational security, OPSEC becomes really difficult when you're developing smart contracts, just because like, hey, I deployed this piece of software that holds $1 million in it, and like, here's my wallet, and so go assume all these things that you could possibly assume. Anyone with an internet connection can do that. Anyone with an internet connection and enough ETH to pay for gas can actually like go and steal your money. So there are definitely some very valid use cases for Tornado Cash. Here's how this is gonna work. We're gonna have like a user, and then we're going to have here's gonna be the pool. So the Tornado Cash pool is gonna be here, and then like a recipient. So like this would, I guess, just be a depositor. So here's the pool. We're gonna have a whole bunch of users send their ERC20 tokens to this pool. And what the docs say here is, it says, to make a deposit, a user generates a secret and sends its hash, called a commitment, along with a deposit amount to the Tornado Cash contract. So if we were to break this down into inputs and outputs, sounds like from the README so far, our input is going to be, we're going to have the secret, which is called which is the hash of, it's a hash of the secret. So a hash of a secret that only I know is called a commitment. So commitments are what's actually stored in the Tornado Cash contract, not balances. Like I said, like a normal vault. Normally it would be like, in like a normal like vault context, like a normal user would have, it'd say like OX, 84 has, 100 ETH. But what it sounds like, what it stores here is, it says like your hashes and commitments are actually what is stored. So we have a hash, and these are maps, by the way, right? So you have a map here that stores a hash of your commitment, so your hash, and then like the amount. We'll see what that looks like when we get into the code. Whoever has this secret can then also be the withdrawer. So the recipient would send in the transaction with the proof that they have the secret and the withdrawal amount, and then they get tokens back. So that's how that's gonna work, right? Secrets are shared off chain, or secrets are just like held by the user. So I keep my secret in my desk or whatever, right? Not saying I've ever used Tornado Cash, but you keep your secret on you in the same way you keep your seed phrase. Or you'd send your secret to your friend so that they can be the recipient on the other end. So the thing is that this secret stays off chain at all times.
Think of the secret as an IOU. So you can go back to Tornado Cash at any time and say, I gave you an ETH, like, this is the secret. This commitment that you have could only have been created by this secret, so you know that you owe me one, and it sends it to you.
Exactly.
Is it like a password, or like how does the user interact with the secret?
So that's the magic of ZK proofs. ZK proofs, just to like give everyone like a quick primer. I did like an applied ZK proof course, and I was surprised at kind of how like simple it was in a way. But I think everyone who likes to talk about ZK proofs be like, oh, I know about ZK proofs, right? So to say very simply, right, like to say very simply, a ZK proof is like, it's proof of honest computation. So like, where else can I do that? Like I give you, Antonio, I give you like, I say, calculate like 7 times 256, right? And then you give me an answer. Well, like, that's the whole point of the blockchain. It's like, where on earth am I able to say like, oh yeah, I can trust Antonio with the answer without having to do the math myself? A zero knowledge proof is you would submit the answer and a proof. So like, and then I don't have to check the work. I just check the proof. So here are some applications. Does everyone, who knows about like how hashing works? Does everyone feel comfortable with the concept of hashing? Okay. So for the folks who don't feel comfortable with hashing, it's just like you can take any amount of data and put it into a hash function. And so like, I could put the, entire contents of like War and Peace, right? I could put like a string that says like, hi, smiley face, into a hash function. What the hash function will do is it will spit out what's called a digest, and that's like, usually, depending on the hash function, it is in Ethereum, a fixed length, array of data, or just like, it can be looked at as a string, right? So it's like, it takes all that information and it deterministically, so it'll happen the same way every single time, hash it into something that is consistent, like, F0, 1, 2, 6, 8. So like those link shorteners use hashes, right? Like you're able to get like a ton of variety in hash functions. So like they don't collide, right? So like maybe so like I can pass kind of any content into a hash function and get like a unique output that's of a fixed length. So when you type in your password on a forum or something online, your password gets hashed and then sent. If it's a good website, like I mean, I don't know. People make weird stuff, but your password gets hashed. They compare your email address with that hash, and they're like, okay, this guy knows the password. Here's the key thing: you can never reverse a hash. So you can't like, someone could be like, oh, you like F01268, and then like figure out what you passed in to the hash function, right? Like hi or War and Peace, right? Like there's no way to reverse a hash function. It's literally like putting a cucumber in a blender. You can never get the cucumber back. I'm over-explaining, but that's as simple as it is, right? Like it's demolished. It's unreversible. So it's a great way to communicate secrets, right? Because you have a hash, right? But those secrets can only be communicated between two parties. It doesn't make sense. Like you can't store the secret in public, right? Like that's the issue with the password database. For example, like if I had a password database that had everything in public, then like my email address, like Colin, at Nielsen.technology, right? It's like the database says that like the hash of my password is like 0x126 blah 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 blah. Imagine if this was public. Anyone could say, hey, I'm Colin R. Nielsen, and the hash of the password is this, right? And you're like, well, like the hash is in public. So we call the part that goes into a hash the preimage. And the really cool thing about ZK proofs is that you can prove that you know the preimage of a hash without revealing what the preimage is. So like to let that sink in a little bit, it allows you to keep secrets in public without having to worry about like access control, because still like you're relying not on the fact that someone showed up like passed the hash into the function call. You're relying that people submit a valid proof that says, hey, I know the preimage of this hash, I know what this secret is, and then you're able to store the hash. So just to like get a all good. Is that making sense to anyone? Is that clicking? Is there anyone that's not making sense to?
I
Give me
don't
feedback.
understand how.
How?
Yeah, I'm thinking of the pre-image as like
Yeah.
a password, right?
Right.
It's like a text-based password.
Yes.
Okay, so
So
I
like
don't know if that's your cliffhanger there. But
the cliffhanger is like the math is insane. Basic like to give like a 20-second sneak peek. I don't know how to do the math myself or by hand or anything like that. But like it has to do with modular arithmetic. So you take a very, very, very large prime number and you make sure that all your program iterations, that the actual like the base system in your programming language is computed against that prime number, and then you use modular math. So you step across the across the computations in that program, but like the return value is always like it's always the modulo. So you can never undo those computation steps. So you end up with steps like I think like you end up with steps across the computation, but they're unreversible. So it's like a way to combine like large prime numbers and modular arithmetic and some other crazy math stuff that goes way over my head, and I'm probably wrong about a lot of this, but like this is like just how I image it. Like imagine if you're able to, because like how like math is always reversible. In this case, like they've created math that have bindings to like steps and programs that is unreversible. So you're able to verify like I'm able to step through the program based on the proof and verify that the output is 1, but I'm not able to infer what the inputs were based on the output of 1. So that's the crazy kind of high level math part. Yes.
So, I mean, I think I understand what you're saying, but you're still interacting with a smart contract.
Correct.
So you still have to send something to a smart contract.
Yes.
So what are you saying?
So-
with a ZK proof, you're not sending the data itself, you're sending the proof of the data. So the commitment in this case is kind of like, I'm gonna vote on something and I'll just like put my vote in an envelope and give it to you. And like, that's commitment. Like, I can't change my vote. Like, I can't change the data I submitted because you have the proof.
Right.
And then like later you can go and open that up and do the computation to say like, okay, like I'm checking it, like this commitment was your vote. Like I can do the computation on your proof now and like know that this is valid in this sense. So it's not that the data itself is being sent. It's
So
a
is
proof
that to say that you have something on your machine that creates that proof and then you just send the proof?
Yes.
Okay.
Yes. So
circuits
for the technical, yeah. So that's what a language is called circom is for. So like just to like draw boundaries here, like this is our on-chain layer, and then this user, what happens here is like off-chain, right? And so like technically, what you do is you build what's called you can use a bunch of different languages for it, but you build these zero-knowledge circuits, which will verify and spit out proofs to you. So what I would do is I would use a circuit. Well, first I would hash my secret, and then I would commit that to the pool, and then like on an off-chain level over here. I would put my secret. Here's how it would look like. I know this is getting a little messy here, so sorry. The secret would go into the circuit, which is a WASM file. So the circuit is compiled down into a WASM file, which is then can be served from anywhere, and I can run it on my client. So I pass inputs in. It does the math to generate a mathematical proof for me. And then out of that circuit, we get the proof, and we get the like the public inputs, so the public stuff, and then we have also like the private inputs. And so what we do with that is we take that and we bundle that as transaction data and create an on-chain transaction. So like you generate that proof, that mathematical proof off-chain, because it's super expensive to do. It's kind of like if you got a lower end device, it's like a kick your fans on kind of thing for a minute, just depending on how like intense it is. So, and then you take that compact proof and then you pass that into the into Tornado Cash. And we'll see what that call data looks like in a minute, but yeah.
Thanks.
Yeah.
So wait, is this running on the front end that when you're interacting with Tornado Cash?
Yes,
And then they also have like a CLI that you could run it from as well.
correct. Yeah, anywhere that can run like a WASM build, which is like any device,
Yeah.
you can compute these proofs. So it's pretty efficient. And then like you get really portable call data, which is then like relatively cheap to verify on chain. So that's the sweet part about like the ZK part. Yeah.
Sweet.
Also, there's a channel on YouTube called DeFi Mook, and they go over this in more detail, and you can pause it and go through some of the stuff. And
Nice.
yeah.
Good stuff.
Yeah.
You could, like if anyone has that, throw it on the HackMD thing. That'd be sweet. Are you not gonna? Oh.
DeFi Mook, like my.
There we go.
There.
Now it's on.
It's on for you?
Yeah, and it's
you just turned it off.
Okay. All right.
Yeah.
It's not on for me. That's weird.
Yeah, there's a specific
Right
thing
here.
about it.
Oh, that's why.
Where's your port?
Any other questions before we move on? Also, like, give me like in-flight feedback here. Do you want to see this go like quicker? Do we want to hop in a code, or is this all helpful stuff? Just like shout it out.
I don't know that we can go quicker.
Okay. All right. Cool. Sweet.
Yeah. Code.
Code.
Let's look at code.
Let's look at code. Okay. Let's go over this last step real quick. So later the user decides to make a withdrawal. To do that, the user should provide a proof that he or she possesses a secret to an unspent commitment within the smart contract's lists of deposit. The ZK Snark technology allows that to happen without revealing which exact deposit the commitment, which corresponds to the secret. The smart contract will check the proof and transfer the deposited funds to the address specified for withdrawal. An external observer will be unable to determine which deposit the withdrawal came from. So I think that's kind of what we covered here, right? Is like I input, I take a secret. The secret's kind of generated for me. I input. I can use my secret myself in 10 days. Withdraw to a different address with that proof that allows me to just keep this as storage on the blockchain. So basically it's saying a hash has 100 ETH. So that allows me to keep this secret in public that says like, okay, an address, a recipient, whoever that is, hash, can withdraw 100 ETH in the pool, and that's what keeps the balances above zero, right? Because if anyone could withdraw from the pool, you'd have a pool with 0 ETH. And that's kind of how that works. So there's no on-chain analysis. It breaks the transaction link between wallets. You can be really stupid with Tornado Cash. You can use it like, okay, I'm not going to tell you how to use Tornado Cash. This is a recording. Figure it out. Think about it. All right. Okay. Right. Just pause. Okay. Yeah, let's hop in a code. Do we mind hitting the lights again?
I have a high level question really quick.
Yeah.
When you say it breaks the connection between wallets,
Uh-huh.
so obviously like when you make a transaction with Ethereum, it's just basically state changes.
Right.
So I guess I think I'm conceptually not understanding from just a high level of if I interact with that Tornado Cash contract, I'm just sending a commitment, not actual ether. And so then if my recipient, I share that secret with them, that just gives them, like how does the state actually change?
I'm sorry.
You are sending Ethereum to their contract.
into the pool.
And they custody it, and the only way to get that Ethereum out is to share your secret key.
Okay, so it's kind of
Yeah.
like let's say I put in like 5 ETH, and then a recipient then gets 5 ETH. They can't really prove it, but someone can kind of be like, oh, it looks like.
Yeah, that's why it's in denominations of like 1, 10, or 100, because if there's
Okay.
10,000 people putting in 1 and taking out 1, you don't know whose 1 is whose.
Oh, okay.
And then there's also the fact that you can't see which, like there's a list of, commitments basically that, okay, if you're one of these, you can take out an ETH. But when I come in and I cash that out and take mine, there's now a new list of who has spent theirs, like who's taken it out. And that list does not directly relate to the first list, so you can't tell who just took theirs out. I can't, If I'm the first person to put one in, and I'm now on the list of who took one out, you can't connect that to the first list.
Okay.
That's through a zero-knowledge proof as well.
Yep. Exactly. Yeah, I forgot to say that in the beginning. That's what breaks the on-chain link is you do send. That's part of the parameters is you send Ether, or you send ERC20 in. Okay, so let's look over real quick the repo. So it looks like we have two folders we're going to look at here. We got contracts and we got circuits. So the circuits are written on Circom, and that's what the client is going to use to generate that proof that they know a secret without revealing that secret. Specifically, it's all really about hashing. And then contracts. There are a couple different contracts in here. We'll go through and we'll take a look. I think probably a good spot to start here is ETH Tornado. I think this is the simple version. Let me set my change workspace to remote. Okay. All right. So, does anyone know if this is the right place to start?
Tornado is the base contract, basically.
Is it Tornado? Tornado's the base contract? Okay. Yeah, so, all right. We've got ETH Tornado, which is most likely the contract that we're going to end up interacting with here. So ETH Tornado is Tornado. So we'll check out the Tornado contract first in this repo to see what's going on behind the scenes. So looks like they've created an abstract contract, which means that usually this is going to be a base contract where you say hey, this contract has this set of functionality, and you're going to use it only in another contract. So this is not a contract. Whenever you see abstract, it would never be a contract that would be deployed by itself. It's always going to be a contract that is included in another contract, which is exactly what we see in terms of ETH Tornado contract. We see that this contract inherits. So we also see that it inherits with Merkle tree with history, and we'll check that out in a second, and reentrancy guard. So looks like a ETH Tornado contract is going to be a culmination of a few different things. And this is where I will flex on Solidity Visual Developer, because I'm able to actually look at the outline of this contract. Why is that not working? I'll click into the editor to. Usually it's it's here in the Explorer. Oh wait. Oh, I put it over here. Oops. Sorry. Stand by. Okay. So here, when you have Solidity Visual Developer installed, you get this very sneaky tab on VS Code called Outline, and you expand that. And what it will do is it'll kind of give you a beat on this contract before you even click into it. So if I go here, I say, okay, here's my ETH Tornado contract. This this up arrow means that it inherits from these types. So it looks like this contract is Merkle tree with history and is Tornado. And I can see all the functions that this contract inherits from, the different references and state changing methods. All these little icons mean something. So a eyeball, it means view. Exclamation point means public. Means external. So it's an external view function called isSpent, right? So I would really recommend this function. This extension here. I put it in the HackerMD notes. It's pretty sweet. We have a constructor here, and we've got only two functions on this. So process deposit and process withdrawal. So that's definitely where the action happens. When I come to ETH, the Tornado Cash, I definitely either want to process a deposit or withdrawal. But let's figure out how that works. let's actually, we will start at the base level here. So process deposit, that's going to be that first transaction on the left. Looks like it's going to require that the ETH the message value is denomination. So message value refers to the amount of ETH sent in the transaction. Denomination looks like an initialization param. So I would set a minimum for this contract. For example, like 1 ETH, right? If anyone wants to get dangerous and send me the Tornado Cash address, I can go check it out on Etherscan and see what that denomination is. You send it to me? The address? Nice. Okay. Is this, oh, perfect. Sweet. So let's do like a little digging here. We'll go to contract, read contract, and we should see denomination right there. And if I look at that number, that unit converter, that's going to be 100 Ether. So I don't know what version of Tornado Cash this is. This is the big boy version of Tornado Cash, I guess. So it requires that you deposit 100 Ether in order to play. So whatever that means, I guess that's they probably deployed a different pool for every denomination to keep things like consistently private.
They deployed other tokens as well.
Okay, got it. So yeah, so this is the big boy zone, 100 ETH only. And then process withdraw. So this function takes a recipient, a relayer. So a relayer, that's a cool layer on here as well. That's just to address one thing. That's to address like when we come to this side on a recipient. Well, what if my recipient is a brand new address? How do I withdraw? Right? I don't have ETH to pay for gas. Like, do I then send ETH for gas from my original user to this user? Because then I now have just created a link and spent all this gas on this private pool, but I still have the link between user A and recipient. So a relayer does is it sits here, and it's like, hey, I'm willing to take some ETH for the gas that I spend to withdraw to you. So it allows me to take, like a zero, a fresh address with 0 ETH, and I can signal a transaction with just my signature. Say, hey, relayer, I want you to withdraw this ETH to me. So I just submit my proof to the relayer, and the relayer will just take a little bit of the funds plus a fee for the kickback for gas, and all that good stuff. So that's kind of what the relayer does. It's like a third party that just holds ETH and executes transactions on behalf of other people. It's a way to get around the whole gas issue, but also, part of that is like they get a little bit of a kickback. So we'll see that exactly right here. So the fee is calculated. The refund is calculated, which is going to be the amount of money that is, I don't know actually what refund is. Looks like refund value is supposed to be 0 for an ETH instance. So maybe that's an ERC20 thing, which makes total sense because ERC20s are not gas tokens. So I guess you would use, you would say like, okay, the relayer would be willing to take 100 USDC for this transaction, even though USDC isn't a gas token. So this is the ETH version. So we're just worrying about ETH, so it can also be used as gas and as currency. So,
Sorry, what is a gas token?
So gas token is ETH.
Okay.
So that's what I was saying. So but Sean had an interesting thought there.
Prior to EIP 1559 last summer, you conceivably could have used anything to get a transaction on chain. You could have Venmo'd a miner and they could have included it, but when 1559 went live, you had to burn ETH to get a transaction online.
There is no other gas token, right?
Yeah. I think Polygon has some kind of shady, cool business going on where you can use USDC, or sorry, Celo allows you to use Celo USD and Celo ETH in order to pay for gas. But in terms of ETH mainnet, you can only pay the gas for a transaction using ETH. unless you have a relayer, then you can pay whatever token or, you know, whatever off-chain
But the
favors. you
relayer
want.
is still paying ETH.
The relayer is still paying ETH. Everyone pays ETH to make a transaction happen on chain.
Every transaction requires ETH. Most people pay ETH. Some
Correct.
people use a relayer and pay them something else, theoretically.
It's a really good way to say it. Concise. Absolutely. This pattern is what is actually used to send the money out for the withdraw. This is, I think, all pretty expected stuff. If the fee is greater than 0, then just pay the fee to the relayer.
Yes,
Yeah, interesting thing about Tornado is the relayers set the fees
Mm,
that for transferring your money to a new wallet.
that's cool. So it's like a free market for fees.
Yeah.
Nice.
Maybe you can also mention on why call is used instead of send or transfer.
Yeah, that's a great note. So the reason why call is being used, and this is a great feature of the Solidity visual developer. Well, yeah. So here we get some insight on this. Returns so it issues a low-level call with the given payload, returns success and the return data, forwards all available gas, adjustable. So call is just the current standard for sending Ether to a contract. So there are a couple other ways that you can send ETH. So we could go like recipient dot transfer denomination minus fee. We could also do recipient dot send denomination versus fee. And these are all ways to tell the EVM to send this contract's balance to whatever this address is. Notice how this is like labeled as an address here.
So what are the use cases?
So the use cases here, transfer has it sends amount of whatever you pass in here to the recipient address, but so here are the two caveats. 1, reverts on failure. 2, only has a 2,300 gas stipend, which is not adjustable. So next is send. This also has a 2,300 gas stipend, not adjustable, but it returns a success boolean. It returns false on failure, does not revert. So here are the different things, right? Like this would fail on insufficient funds. So like it would revert. This would just this call here would return false for insufficient funds.
What's the difference in the real world experience of that?
Yeah. Okay. Great point. So I think the biggest difference is it has to do with the gas stipend. So transfer and sending ETH to another contract can actually trigger a response on behalf of that recipient. So the perfect example of this is a Gnosis safe. You can build custom functionality onto a Gnosis safe, which is a very commonly used wallet. It's a type of wallet that when it receives funds, it actually calls its own function, right? So you could write some cool module on a Gnosis safe that's like, when it receives funds, it processes those funds and maybe splits it evenly between all the DAO members. That'd be a super applicable use case, right? So that like a Gnosis safe would never hold funds. It just, whenever it receives anything, it just splits it instantly between all the people who were signers. That'd be like a common use case. I could see people doing that. But that computation is gonna take gas. So if you're using transfer or send, you're only gonna create a new transaction that has 2,300 gas to play with. And so like if you do something on the receiving side that takes 4,000, you have 40,000 gas, that's gonna fail regardless.
Yeah, a single S store is like 21,000 gas.
Yeah, exactly. It's like hardly anything. It's just enough to receive. I think it's barely enough to revert, honestly.
You can knit logs, that's about it.
Yeah, logs are 5K. So unfortunately, no.
Yeah, you can.
You can on receive?
Yeah,
Oh, cool. All right. Dang.
they've lowered the gas cost for logs.
Oh, they have.
Believe so.
Sick, dude. Nice. Good lore. Good lore. So call is the way to go because it allows your smart contracts to be less brittle and more composable. It's a little dangerous. It's a little close to the metal, and you have to watch where you put it because of a thing called reentrancy. So like what I said, like the recipient, like imagine if you had a contract called recipient here, and there are two reserved space, GitHub Copilot already knows what I want to do here. There are two function names with reserved namespaces in Solidity, one called receive and one called, let's see, GitHub Copilot, nope, fallback. So these functions will be called automatically whenever a function, oh no, I lost my, 1 second. Wow. My computer is really annoyed. Give me 1 second. But you have two like reserved namespaces functions that one is just for receiving ether. So that's just called the receive function. And one is for receiving any kind of transaction. And that's how proxies work. So that's called fallback. Okay, click share.
And what happens if you don't have those in your smart contract?
Then they'll just receive ether like normal.
But you can't get it out.
Unless you have a function to withdraw.
Unless you have function withdraw.
Correct.
You can only receive them to payable functions or on self-destruct of a different contract.
Correct. Yeah, that's an important caveat. Is you never want to say that there's logic in your contract that requires that you never receive ether, because someone can always maliciously send you ether. So that's a big security concern. Shoot, man, what the heck? So yeah, you always want to make sure that you allow as much gas. You just want to allow all the gas, because it's up to the user to specify how much gas they want to initialize the transaction with. And that user is computing how much gas that transaction will actually need off-chain. So that's what your MetaMask does, is it computes, hey, how much gas should this transaction take? And then it forwards that amount of gas in Ether when it goes to like execute the transaction. That's why sometimes your MetaMask kind of like sits there and blinks for a minute, because it's calculating the gas. That's also how your MetaMask fails before running a transaction. Like before even posting it on the blockchain, is because it will run that transaction locally to see if it works. I don't know if you guys have ever wondered that, but yeah. All right, we're gonna try this one more time, and if this fails, then we're gonna have Dan run off my live stream.
Is it always a perfect amount of gas, or is there ever like a little that isn't, I don't know, the MetaMask like estimates wrong?
Yeah, there usually is, but all overspent gas is forwarded back to the initiator. So you get that.
Okay, so
Get
they'll
that
take a
refund.
little off the top and be like, oh, we're good.
Yeah, right. Yeah, no, well, I mean, it depends on your wallet. Maybe your wallet's really malicious, but so yeah, okay. Let's.
That's why I read.
All right, sweet. And we're in here till 8:30, so we're good. Thank you. Okay. All right. Now we're ready for the Tornado Cash contract itself. So maybe I'll try to go a little bit more at like a high level with this stuff, so that we can get through. So you have nullifier hashes, and we have commitments. Those are the two main things being stored on this contract. Nullifier hash is just to say that a commitment has been used privately. So we'll see how that's used in a minute. And then commitment is kind of what we talked about before, is it said one mistake that we made in the diagram here is I said that a hash was mapped to a balance. Looks like this is actually mapped 1-to-1. So since this is a pool that's denominated only in 100 ETH deposits, that like it's assumed that every single commitment hash is going to be 100 ETH.
Value.
So you could withdraw 100 ETH as long as you have a valid commitment nullifier hash. We've got some events here that signal that it happened on chain. What happened on chain? So the commitment. Note that all these are like bytes 32. So that's just like a 256-bit, 32-byte hash. So whenever you use the function cacac 256 on something or any other kind of hashing algorithm that packs down into 32 bytes, that's going to be that width. It's going to be that amount of size. The EVM works on 32-byte slots, unlike I think any other like VM, and that's because it works really, really well with elliptic curve cryptography. So elliptic curve cryptography is a compact way to have the same amount of security as like 4096-bit RSA. So very, very, very big numbers. Elliptic curve solved the problem of having the same amount of security for like industry standard systems, but in a much more compact way. So the EVM kind of works on this idea of elliptic curve cryptography. And so that's why we have everything in like spaces of 32 bytes. Call data works on 32 bytes. Storage works on 32 bytes, etc.
Is that the default one you pass when you just type something as bytes?
No.
Yeah.
So there are two different types. There's going to be there's bytes. Whenever you type the word bytes, that's actually a reference type. So it's a reference to a n amount of length array of data in the memory or in storage. And the EVM has special instructions for handling variable amount references. When you say bytes 32, that's a primitive type. That's a fixed type. It has one destination in memory, one destination, and like kind of the normal assignment slot in storage. So I'm going to use my Solidity visual auditor here. So if I go to outline and we're looking at the tornado function here. So here are all my contracts. I get lost when I scroll through code, so this really helps me. So it looks like we got a deposit, process deposit, which is like the internal version. That's signified by the lock emoji. This is the external version. So probably this is going to be the pattern where deposit is calling process deposit, withdraw is calling process withdraw, and then we've got some view methods here, which are like helper methods. So yeah, that looks like how the EVM is handling that. Sorry, not the EVM, but it looks like how this contract is kind of handling withdrawals. Oh, okay. I see how this works. So this is an interesting inheritance model. So if we noticed, I'm going to bring this up side by side here. Inheritance is kind of, I think, the funkiest thing in Solidity to kind of wrap your head around. But on the Tornado contract, it's an abstract contract that says, hey, every contract that is Tornado, regardless of token, regardless of amount, denomination, etc., is going to have a public external payable deposit function. But how that's actually handled is different depending on the implementation. So see how this calls process? Oh no, it's going for you too. Okay.
Is anyone not familiar with abstraction as a design pattern? So the reason you might use that would be, it's like, I'm gonna create something, but it's more of an idea of something. It can't actually be instantiated. What you would do is, you would inherit all the code from that abstract,
It's gonna turn solid.
function, and you would put it into, a child where you can instantiate it. And the reason you might wanna do that is, if I need to write 10 Tornado Cash contracts, and parts of them are all the same, I can reuse that code by putting it in an abstract one, and then pull the code into each of those instead of writing it every single time for these. So that's kind of the reason you might want to use something like that, and that's why Tornado Cash does it, because they have a different contract for 1 ETH, 10 ETH, 100 ETH, 100 USDC, 1,000 USDC, all these. So it's just like making the code a little more reusable in that sense.
Mm-hmm. Exactly. It's a way to say, like, as programmers, when we design systems that are composable, which means can be used across a lot of different instances, is that you say, all right, what is primitive about this one thing? And then you break it down, right? Like, okay, I have you would probably have, like, say you have 5 different map apps. You have Brave Maps, you have, Leaflet, you have Google Maps, right? And you can run them on your phone and you can use them to navigate. The commonality in all those apps is the fact that they measure your speed and measure where you turn. So if you can write a function that handles when you should turn and handles how fast you're going in all cases, then it doesn't matter what your implementer does. So the very, very, very top layer of your program, which is going to be the Brave Maps, the Apple Maps, the Google Maps, all they have to do is implement that check speed, because the programmers figured out there's something about check speed that is consistent across the board, regardless of how the program is implemented. So how's that going, Brian? Maybe you guys just all have to go to my live stream. Sorry. I know that kind of sucks.
Pop those numbers.
Brian, try passing that back to me real quick. But yeah, so what this looks like in the is that, like, they have a that is Tornado contract, and they have a Tornado ETH and a Tornado ERC20. And on Tornado ERC20, that's going to handle process deposit differently, because the way that ERC20s are transferred are fundamentally different. So that's kind of why. Like, it's very simple to process an ETH transfer, but you have to do a little bit more checking when you process an ERC20 transfer. All right, I don't know how much time I've got here, but we're gonna just try. There you go. So, and that's all delineated based on the override. I would get your guys' stream up if you can. I think, like, it'll probably die in a few minutes, but this is all this is all handled in the process deposit. So notice how this is an override function. So we define a virtual function here that says, hey, for any contract that wants to be a Tornado contract, like this one is Tornado, it has to override process deposit. So notice if we didn't have process deposit in here, and my IDE wasn't being ridiculous, version 7. All right, let's see if that works. Then you'll notice I should get an error here. Maybe it's because of this contract. Yeah. I should get an error on this contract that says, if you've ever seen that infuriating contract should be marked as abstract error message, that's because there is a base contract you're inheriting from that you've not fulfilled the requirements of what it means to be a Tornado contract, which is to actually say that, okay, I override the process deposit.
Can you explain virtual real quick?
Yeah, virtual is a marker. It's like a UI flag that allows you to say that a contract needs to override a certain method in one way, or sorry, can override a certain method. So virtual flags that a contract can override a certain method. The fact that this function needs to be overridden is determined by the fact that it is unimplemented. So this is an abstract contract. Like this is a stub, right? There's not even a function body. It's not even a no-op. It's literally like just straight up unimplemented. So like this would be much different. This is an unimplemented contract that says, okay, like this is actually a function that a user can call if it wasn't internal.
It does nothing.
It does nothing. It's a no-op,
It's a
right?
placeholder.
Exactly. But virtual, like a virtual unimplemented contract says, hey, whoever inherits from me needs to actually override me. So any contract, any function that you want to override the functionality of, you have to mark as override, and then your internal function is marked as virtual. If you use Open Zeppelin contracts, that's how this works with like hooks and transfer functions, is that you have to say like, okay, I like this functionality, but I'm going to override it. And this stuff just comes with time. Like I said, like inheritance is the weirdest part, I think, or one of the harder parts of Solidity is figuring out like where your functions come from and not shooting yourself in the foot because of it. Okay, finally, we have reached the good part. So this is the withdraw function. This is where the magic happens. So this says withdraw a deposit from the contract. Proof is a ZK snark proof data. And input is an array of circuit public inputs. An input consists of a Merkle tree root, hash of all the unique deposit, nullifiers to prevent double spend, and the recipient of the funds, and an optional fee that goes to the sender, usually a relayer. You could also have the relayer be your friend and have him do it for free because he likes you. So this here, this is the ZK proof. This is the thing that's generated off-chain, like in our diagram, and passed in. How I'm going to explain like root nullifier hashes and membership proving is by saying like, let's just think about it in terms of arrays. So like you have an array. I think everyone's probably familiar with and comfortable with the idea of an array. And if you're not, it's just a list, right? So you've got this array. How do you have a compact proof that an array has been unchanged is you can use hashing. And so like if you want some cool homework, go and mess around with Merkle trees. Merkle trees is a really easy way to say like actually the current state of a blockchain, the entire Ethereum blockchain, everything that's ever happened on the Ethereum blockchain is validated by one 32-byte Merkle root. That is the culmination of everything that's ever been done. Every single byte that's been done on chain has been hashed together into a Merkle root that verifies the current state, right? And so it's like in the case of Tornado Cash, you put yourself in this like array that says, hey, this is an array of recipients, right? And then I am a valid withdrawer. And we'll see how that works here in a second. And that's that whole Merkle tree with history piece of code that we're inheriting from that gives us access to some of these functions. So like another shill to the Solidity visual auditor or developer thing is we see where the state var comes from. It's inherited. It comes off of Merkle tree with history, and it's a function call. And here's the declaration. I can jump to it. Sick tool. So what we're going to do is we're going to verify. I guess let's look at what this does. So first, it makes sure that the fee is less than or equal to the denomination, which would be crazy that a relayer would charge more than 100 ETH to withdraw 100 ETH, but you just have to have those sanity checks in there. Next, it checks that the nullifier hash, which is like, is every raise a show of hands who's familiar with an N once, like a nonce. Nonce, yeah, nonce. Okay, so a nonce is like something that your wallet has a nonce. So on the Ethereum blockchain, it is just an auto-incrementing number of how many transactions you've done. And why this is important is it avoids someone else replaying your transaction, because anyone can grab your transaction data and submit it. So when I submit my transaction to the blockchain, I say, hey, I'm calling, this is my wallet, I know a private key, and I want to do this on behalf of my wallet. You submit that, and then your nonce is incremented once that transaction goes through. When that transaction is confirmed, your nonce gets incremented, and so no one can go and try to do that past transaction twice. So a nullifier hash, kind of by the name, it's actually well named, is kind of the same way, right? It prevents me from going back and trying to do this withdrawal twice, even though it's in secret.
Where's a nonce stored?
The nonce is actually part of the. I'm glad you asked. The nonce is actually part of the storage for an address. So there's this great blog that I pulled up here, which I reference very often. It's a Notion page. It's actually called the EVM Handbook, and there are all these references in here. I'm going to put this on the Notion page. Oh, nice. People have been filling this out. This is great.
Where's the link?
It's in the it's in the meetup. EVM Handbook. So this is pretty sweet. Go check that out. But oh, dang it. Every single run it back. I guess this is a good break to talk about this. So an account on Ethereum, an address of either like a smart contract or a externally owned account, or an EOA, which is a wallet like you and me. That's how we interact with the blockchain. Our wallets have no code, and they have a nonce. Smart contracts have code, a nonce, an address, a storage, like a state root hash, and something else. Here, go to your desktop and open up the it's like gonna look like a USB in Finder, and you have to open up click shift, and then open up the OSX one. Smart contract storage versus account storage, kind of different, but both of them have a nonce that allow the things that they do on their own behalf to only happen once, and that's what keeps them. That's what keeps it private. And so I dropped that EVM handbook in there, and that explains. Here we go. I think you have to hit the live button down on the bottom left. Yep. That should be it. And then I should be.
Hit live again.
Maybe refresh. Yeah, we should get this figured out before next time. Sorry, guys. But what I'm pulling up now. Are we done? Is the stream over?
Is this the right one?
Is it working for other people? Yeah. The stream is? Oh yeah, it's working for me.
Hey, there it is. All right.
Cool. Sweet. All right. Yeah, we are. So here's an account state. There's a nonce, a balance, a storage root hash, and a code hash. And so this will explain kind of the different types of how the Ethereum stores account data. But yeah, the TLDR is you need that nonce. And so the nullifier hash is similar, but you need your own custom nonce in a private system, or else everyone can go back and try to replay transactions. So that's why we check on line 86 that the nullifier hash has not been used. Because if you see on line 96, when this transaction executes, the nullifier hash will be set to true. So it says, hey, this private note, which is kept secret by the hash, has been spent. And that's what makes the system so simple. 100 ETH can go in, 100 ETH can come out. When 100 ETH comes out with a secret, it just like spends that secret note without revealing what the note is. And then this is all the Merkle proof stuff. This is also a virtual function. So I think the rest of this are just view. So this is really what kind of this is the core of the contract. Is it checks, and I know I'm a few seconds behind here, unfortunately, but this is the core of the contract. Is it accepts a ZK proof, the root, the nullifier hash, the recipient, the relayer, the fee, and the refund. And so just to go a little bit deeper into ZK just real quick, the proof is verified by the verifier, which is auto-generated based on the ZK circuit you build. So this is the private input, kind of like was mentioned here, right? And this is the public input. So the proof keeps the secret in private, but it checks it against the root and the nullifier, the recipient, the relayer, and the refund. That was a ton. Just to get a pulse check, like, where's the room at? How are we feeling? Do we want to go more into the circuit side of things, the ZK side of things? Like,
Where's the commitment used in this withdrawal? I guess it can be if you
so the commitment actually happens at the deposit.
right.
I think that, is it the nullifier hash that?
I believe the commitment, yeah, I think that the commitment is shielded in some way.
Just so you can't deposit twice, I guess, on the same secret.
I think, yeah, and I think it's shielded based on I think you hash, oh yeah, right, because remember from the README, the commitment is the hash of the secret. So the commitment is kept separate from the, what is this called? The nullifier hash.
Yeah, you can't use it in a withdrawal, otherwise there'd be a direct link.
Correct, or else there would be that, exactly that. There'd be that direct link.
Do you know if this contract is already deployed to the Coven testnet?
Yes. Yeah, so all these contracts are immutable and they're out there in the wild, and anyone can go mess with them. It's very illegal for us to do it in a public way, like on mainnet with real funds as American citizens. But
it's on the Coven testnet, so is there like an address that we can get to?
yeah, I think so.
It's on a Coven testnet, just maybe spin up a wallet that you don't care if it can no longer interact with other things.
Right.
You can actually still, even as US says, we can still interact with TraderCash because some well sent like 0.1 ETH to just tons of addresses just to prove that it can be done.
Is there a faucet for the Coven ETH that you can use?
No, Coven's been
It's,
deprecated.
Gorley or
Yeah, you're
Sephora.
I'm sure someone's done it on Gorley. And if anyone needs Gorley ETH, I have 20, so hit me up.
Oh, it's on Gorley too?
Maybe. I'm sure someone's deployed it. I'm
Can you
sure.
walk into the verifier interface?
Yeah,
Sorry, library.
absolutely.
They've got a couple other contracts in there.
I think these are only I think these are the key ones, is like literally Tornado and then whatever inheritor. I don't know what C Tornado is. Governance compound. Yeah, it's the governance. Okay.
Gotcha, yeah.
Yeah, so let's hop into the verifier.
My guess is this is assembly, let's see.
Yep. And so this was this was kind of proposed in I think it was like EIP 39 or something like that, where there's like a special backdoor EVM code to compute like prime like G pairings or whatever on an elliptic curve for 0k proof, like ZK proof. So like Vitalik laid the groundwork to be able to compute and verify zero knowledge proofs on chain like 4 or 5 years ago. Thanks so much for coming. See ya. No, please. Yeah, bye. And then so this kind of uses definitely some low level stuff. So let's look at our like lovely little tool again, add an outline. So it kind of uses these, here's the verifier contract. It's got these constants. So snark scalar field and prime q. One thing that's super interesting about these numbers is that they are the largest prime number that you can fit into a 256-bit slot. So it is like it kind of sets up the ZK system to work around like, and if you think of modular math, right? You're when you modulo anything, you're essentially like, you can imagine like setting a clock, right? Like so our any numbers that we use is like mod 12, right? Like on a clock. So it's like you're setting these computations to kind of work on a certain prime field. And so this one is just happens to be the closest prime number. It comes out to about 2 to the 254. So it's really close to 256, but the next prime number I think goes above 256. So just like kind of some fun stuff there. So success. Static call. I believe. Let's see, what does static call take? Gas address. Okay, so this is the actual low level call. It takes all these different pairings and it passes it to a contract, which is a precompile contract. So Ethereum precompiled contracts. Whenever you use recover, like EC recover, that's going to be like you're actually sending a call to address 1. And this will come up in a second. Sorry, a little behind. You're actually sending a call to address number 1 because there's a precompiled contract that knows how to recover an address based on a signature. And so like there are all these EIPs that work based on like the blockchain saying, okay, all right, address 1 has this code on it that does these different things. So here we see address 8, checking a pairing equation on the curve alt BN 128. So, and that was like, EIP 197. So it was actually like quite a bit farther along. But yeah, so this is what I was talking about. Vitalik put that in, and it's the real horsepower that allows us to compute zero knowledge proofs on chain. And if you see static call, the second, argument in here is going to be the, waiting for this to catch up, is going to be the address. And so we make a call to address 8 we make a low level call to address 8 to check to see if our zero knowledge proof is valid. So as you can see, this stuff is kind of redonkulous. Verifying proof, it's super goofy. But like this is your private key, this is your private stuff, this is your public stuff, and you need your private stuff to be the secret, and you need your public stuff to be the resulting hash. That's kind of like the TLDR is, like we talked about earlier, ZK proofs allow us to store hashes or allow us to use hashes as secrets that are kept in public. I can create a system that keeps a hash on the table for all you guys to see, but the only way to get through the door is to submit a valid proof that says that you know the preimage of that hash. So this is kind of the exact same thing. Is it's like you got to make sure that your public inputs and your private inputs are that they match, and then kind of this special wild moon magic is what Vitalik calls it. will compute to see if you computed that honestly.
Does this pair with the circom files?
Correct. It does. So when let's kind of like look at the circom files. I won't go too deep into it because it's like a totally different language. But So, yeah, it's a really, really goofy language. You'll see it come up in a second. Yeah, so you have a template, and you have inputs, and you have outputs, right? So I have a nullifier input and a secret. So I know the nullifier and I know the secret, and that is a private input. These are all hash functions. So there are, just like we have KeyCac 256 on Ethereum, there are circuit optimized hash functions like Peterson and Poseidon and Mimic Sponge are to name a few. And kind of all this goofiness computes on your machine, and it says what it's going to do is it's going to hash your commitment hash and your nullifier together. So you keep that secret and you use the nullifier for obscurity, and then you get a commitment and a nullifier hash. So notice how like this is a nullifier, not nullifier hash. So in terms of the secrets that I have a secret which is my nullifier, and I have a secret which is my actual secret key, like a password or something like that. And from that, so I guess like if we were to go back to like the classic coding interview style of programming, right? It's like you have your inputs and you have your outputs. So like my input's going to be my nullifier that I choose and my secret key that I choose. And because of ZK magic, the input stays private, and the output is public. Well, it's private, but publicly provable. Publicly, that's not spelled right. So the outputs, as we can see from this template that Circom gives us, is going to be our commitment, which we are going to send to our friend, and which will be stored in the smart contract, and the nullifier hash, which will be used when I withdraw, almost consumed even. So that's kind of how this is going to work. Like, this is all goofy stuff to do a hash function. The reason why this sucks so much is because there are actually no if statements in Circom, because it has to be completely, I forget what the word is.
Recursive?
No, it's not recursive, because Circom isn't recursive. Other ZK languages are, yeah, they're non-branching. So it has to be completely flat. Everything has to be known at compile time. And then this is just like the individual, this like commitment hasher is used n amount of times to compute the root of the Merkle tree. So all this stuff is like a complex, hashy way of saying that I am in the withdraw list. I'm on the secret list, but not revealing who I am. And I say that I do that, and I get my withdrawal ticket by generating a proof out of this. We're about to run out of time, so the last thing I'll show is just like kind of what those like little elements look like, because I know it's still hyper abstracted. But yeah, any questions in the meantime?
I'm just wondering, are we gonna be responsible for writing these like Circom files when like zero knowledge proofs become a thing that we have to do or interact with?
So luckily, I think that like one thing that I learned doing Circom stuff is that CD ZK is that actually kind of everything, you don't really need to write much in Circom. Everything there are all these primitives, like for example, hashing ZK Merkle tree, there it is. ZK Merkle proof, okay, yeah. There are all these primitives in the same way that we use like Open Zeppelin for primitives. Like, no one needs to really roll their own ERC20 anymore. in the same way, it's really like no one needs to roll their own ZK circuits anymore. It's all pretty straightforward. Yeah. Any other questions, real quick?
I have just a high level architecture question on the Circom. So how does that actually get passed into the actual smart contracts? How does, because that computation happens locally off chain, let's say.
Correct.
So then how does that get into the?
So, I mean, I think it's just in the same way, maybe this is not answering your question, but I think in the same way that I have a smart contract that builds a transaction off chain before it sends it on chain, it'd be the same way, right? I get the input parameters based on my local machine. I just have to do a little bit more work for it, if that makes sense.
So it's not just something like call data within a function?
No, it's not. Well, wait. Yeah, it is, but it's computed off chain, right? So it's computed to me off chain. I'll show you exactly what this looks like, and tests are really helpful for implementation references. So when I compile, this is my compile script. When I compile a ZK proof, I use the Circum CLI tool, and I actually get a WASM output into a build folder. And so see this Merkle tree JS in my, wait, you'll see it right here in a second, coming up, build Merkle tree JS. I get this folder here, and that's my WASM file. So I can actually load that WASM file up on the client and pass these inputs. I can't load it up in here, but basically I could use file system to read the buffer and then calculate the witness based on that WASM file. And so I just pass an input, and then I get an output. So that's kind of how it works on the on that side of things. Then there are a few things I have to do to kind of package up my circuit from a developer level. But essentially, what I'll get after I run this script is I get a Merkle proof verifier that is going to be built in Solidity based on whatever Circum circuit I have. So it's domain specific. The Merkle proof verifier is 1-to-1 based on whatever circuit you wrote. And then I also get my WASM build, and that's and then I use that verifier to I say Merkle tree is verifier, and then I can call the verify proof function. And so this is literally what this is kind of how more modern Circom works with what's called a Groth 16 proof, is that I literally just get arrays of 256-bit numbers, and those are my steps that the program needs to prove, and then this is my public input. So my public input is the root, and I just prove that this proof passes, that it makes sense. The Solidity part kind of does its thing, and then I'm able to prove that I'm part of this special membership crowd without revealing what my underlying identity is, just based on these proofs. So the test is here. This is probably super helpful. Okay. Okay. Input signals. So this is how the front end would work. Here, give it. It's the last part, and then we'll end here. Okay. But yeah, it all kind of culminates in this last function that you'll see here in the tests. Click share, and for Mac OS X. Three, 2, 1. Connecting the base unit.
So when's part 2?
Right? Actually, I think this will kind of cover it from like a high level, unless we want to do an entire ZK course. But so here we go. We got Groth 16, which comes from the Snark.js library, and we asked the Groth 16 JS library to do a full proof based on public inputs, which, as we determined here, are going to be my, the commitment and the nullifier hash are going to be the public inputs, the public signals. Then I pass that WASM file, which does the heavy computational lift of computing the zero knowledge proof off chain. And then I get this thing called a Z key, which is just like, I kind of forget exactly what this is, but it's like a necessary secondary part. And what I get here is a proof. And so, oh yeah, this is super dumb the way I'm doing this, but it's just because the the library is written by some scientists and it's in JavaScript and it's terrible. So I do this dumb thing to like make it nice. But literally, I'll get numbers. I will get an array like this proof object that is returned after I await this Groth 16 full proof. I'll get this public signals and a proof. And then what I can do with those public signals and that proof is it literally looks like this. It looks like, I think it's at the very end here, verify proof. So proof is an array where the first index is a tuple of 2. Then there's a second array where it's like tuple again. All right, that's it. That's pretty much it. So it's like you get these magic numbers, and then like you pass it to Groth 16, it goes to the input, it computes that weird modular arithmetic thing, and then you're able to prove. Did you just straight up do it?
To answer the
Legend.
Fucking magic, bro.
magic question, you're basically passing it to that address 1, right? In the end, that
You're doing a low-level call to address 8 with some special numbers.
Address 8 is the ZK.
It's the precompile for proving that points exist on a certain curve.
Light warning.
How much did we need to turn off the lights?
Thank you, man.
Yeah. I don't know if that's helpful, but there we go.